This is number 1 from AP FRQ review, derivative graphs. So it says the figure to the right shows the graph of f prime, the derivative of a twice differentiable function. Twice differentiable again just means that it's a smooth curve, that the second derivative function exists, and it's not going to be a it's going to be a polynomial with at least degree 2. On the interval from -3 to 4, the graph f prime has horizontal tangents at -1, slope 0, at x equals 1, and at 3. The area is bounded by the x-axis, and the graph of f prime in the interval from -2 to 1 is going to have area of 9. But because we're dealing with definite integrals, we're going to go ahead and assign that to be a -9, since these are all accumulations of negative y values, and 12 respectively for the region from 1 to 4. So the area is 12, but below the x-axis we'll go ahead and mark that as -12. Find all the x-coordinates at which the graph of f has a relative max. Give reasons for your answer. So we know that we're going to have to deal with our f prime graph. We have to be able to interpret it appropriately. So I'm going to go ahead and mark, label the parts of my f prime graph. Anything that's sitting above the x-axis, I know it's going to represent visually a positive slope for the original graph. And any portions that's below the x-axis will indicate places where the original graph is going to exhibit negative slope. And anything that lands on the x-axis will indicate where my original graph will have a slope of 0. Could be relative max, could be relative mins. These are going to be at least candidates where that could happen. I like to go ahead and just create my slope sign lines. My endpoints are -3 and 4, x values of -3 and 4. Between -3 and -2, I see that this portion above the x-axis represents positive slope. So I'll go ahead and just give us a visual, create positive arrow with representing positive slope. Between -2 and -1, all these portions of graph are sitting below the x-axis, so we'll go ahead and mark that as negative slope. And then between -1 and 4, between +1 and 4, still below the x-axis. So if we want to find relative max, we can kind of visualize how this original f of x graph could look like. Rising between -3 and -2, hits a relative max, decreases to some place where at 1 where it's going to become a slope of 0, and then continue to decrease. So this graph was going to have a relative max at x equals -2 because f prime changes from positive to negative. Okay, for part B, indicate where our graph is concave down and decreasing. So to gather information about concavity, I'm going to create a second derivative sign line. So basically all the peaks and valleys, all the relative max and relative mins of my f prime graph are going to serve as points of inflection for my original graph. So I'm also marking my points of inflection, which is not what part B is asking, but gives us some, allows us to mark off some points to indicate where our concavity behaviors will exist. So between -3 and -1, whenever I have negative slope off my f prime graph, that's going to represent where my original graph is going to be concave down. Wherever my f prime graph has positive slope, that's going to indicate where my concavity is going to be, my graph is going to be concave up. Negative slope, concave down. Positive slope, concave up. Just going to go ahead and make those indications on my concavity sign line. So I'm looking for a place where the graph is concave down and decreasing. So I'm going to go ahead and just put these two slope and concavity sign lines, kind of stack them on top of one another, and look for places where I have decreasing slope and concave down. So concave down and decreasing slope looks like they're going to overlap in the intervals from -2 to -1. And then also again from 1 to 3 is where we have that matching or that lining up of decreasing slope and concave down. Okay. Part C, Points of inflection, we can pull that information directly from the second derivative sign line. Because there's a change in concavity, we know there's points of inflection at -1, 1, and 3, because f prime either changes signs from positive to negative or from negative to positive. Or f double prime changes from positive to negative or negative to positive. Or we can say f prime changes from either increase to decrease or from decrease to increase. Okay, for part D, given that f of 1 equals 3, write an expression for f of x that involves the integral, find f of 2, and find f of -2. So if we anytime we want to look for a position given a starting point, and we're provided some derivative graph information, we can think of it this way. And this is a rearranging of the first theorem of calculus, but this is useful for especially if we're looking for a specific point or for problems that involve particle motion. If I'm looking for a final position, f of b, I can think of it as my initial or given position, f of a, plus the displacement, which is filling in the gap between my starting and my ending point. So in this case, I'm looking for f of 4 and f of 2 and f of -2. Okay, part D. Find f of 4 and find f of -2. So to find f of 4, I'm going to start off with f of 1 because f of 1 is a ordered pair that's provided for us, right? Part D tells us that f of 1 is equal to 3. So I'm starting at f of 1, I'm trying to get to f of 4, and to bridge that gap, I have to find the definite integral from 1 to 4 of f prime of x dx. So f of 1 is equal to 3. The integral from 1 to 4, we look at our graph. Integral from 1 to 4 is a region below the x-axis, area of 12, but definite integral of -12. So we say 3 plus -12, which is equal to -9. To find f of -2, again, we start at our given or starting position, f of 1, plus the integral from 1 to -2. So we're working backwards here. We're starting at 1 and we're working backwards to -2. But this is where I would prefer to, once I have this down on paper, I want to make sure that my bounds are from smaller to larger. Preferably just easier, more straightforward if we can read the graph from left to right rather than reading from backwards from right to left. So I'm going to flip the bounds so that I can make that adjustment. But if I flip the bounds, I have to make sure that I'm not changing the overall value of this expression. So I'm going to pull a negative out in front. So I'm going to change the sign and then follow it, balancing out with flipping the bounds. So now I can read this more straightforward. The integral from -2 to 1 is just going to be what we have on our graph here. From -2 to 1 is going to be a -9. So I'll replace that integral with a -9. But because we changed the sign to a negative, I have to keep track of that negative as well. So 3 minus a -9, the two negatives become positive. We get 3 plus 9, which is 12.